Good afternoon. Let's continue with our discussion of semiconductors. Today is going to be dope. Just pun intended. Talking about doping, semiconductor doping. Yeah, literally, they couldn't find any other word. All right, let's go to our notebook. Let's see. Device verification. Stop here. Oh, before we proceed, anybody have any questions about intrinsic semiconductors? Okay. Right. Oh, by the way, let me remind you of the rules again. No food or drink except for hard cap water bottles. Okay. If you have liquids with soft lids, please leave it outside the classroom. Not here. Not on the carpet. All right. So this was the equation, or this is the equation for intrinsic carrier density. Okay. Intrinsic carrier density. Ni square is BT cube e raised to minus EG over KT per centimeter raised to 6. Okay. All right. Ni stands for the intrinsic carrier numbers. N just by itself refers to electrons. P just by itself refers to holes. For every electron that moves free, or for every free electron, there is a corresponding hole that is created. And so the number of electrons and holes are always equal in an intrinsic semiconductor. Intrinsic semiconductor is where you have electron hole pair generation solely due to thermal effects. The product of N and P gives us Ni square. Okay. All right, so let's take a look at the components of this equation. We have B, we have T, K, and Eg, 4 of them. Eg is something we already looked at a few slides ago. That's the energy band gap, or the band gap energy, defined in electron volts. K is the Boltzmann's constant, 8.62 10 to minus 5 electron volts per Kelvin. T is the absolute temperature in Kelvin. And B is a material dependent parameter. Okay, material dependent parameter, which for silicon, germanium, and for gallium arsenide is listed here. B as well as the band gap energy. So there is a solved example in the book. And so I'm going to ask students to review the solved example. For the most part, this is straightforward. If you are asked to calculate the intrinsic carrier density at any given temperature for any given material, simply plug in the values, because Eg is known to us, the T is known to us, K, the Boltzmann's constant, is known to us, and so is the B, material dependent parameter. So it's simply plug and calculate. Okay. So the next slide shows a graph or a chart outlining the number of intrinsic carriers for 3 most common semiconductors: germanium, silicon, and gallium arsenide. Table lists both B as well as Eg. So what do you notice? Let's take a pause while you go through it. What do you notice? Which is, of course, something also that we have already talked about. We were at absolute zero. Everything was frozen. Absolutely. Right? So you are at absolute zero. temperature was, everything was frozen in place. As the temperature rises, more carriers are generated. So this graph seems counterintuitive because it's starting with a high number on the left, going down to low temperatures on the right. And you can see with decreasing temperature, the intrinsic carrier concentration decreases. Okay, what else? What else do we see? Not just the graph, also look at the table. What do you see? One person sees that, right? Germanium has the lowest band gap energy. Gallium arsenide has the highest out of these three. And so when we create devices, it doesn't require much energy for that band gap to be overcome. Meaning a small voltage that's applied for the device will get it conducting. This has both pros and cons, depending on our application, of course. And if you think back a few slides ago, a few slides earlier than this, we spoke about how carbon is also from column 4 of the periodic table, but yet it is not a semiconductor because the band gap energy is too large to be overcome. So it can act as an insulator, but it cannot act as a semiconductor. We combine carbon with other different compounds, and we can create a compound semiconductor, but carbon by itself is not a semiconductor. Carbon, by the way, is also, depending on the form it takes, it can be very stable, and the bonds can be very hard to break. Okay, so carbon in certain amorphous form can form graphite, but under the right conditions, very high pressure, very high temperature, it can form diamonds. All diamonds are just naturally occurring, or naturally occurring diamonds are just carbon that are under a huge amount of pressure deep within the Earth's crust. And so over a long period of time, suitable pressure and temperature, it forms a very stable bond, turns into diamond. That is also how lab diamonds are created. You have a CVD chamber. Well, chemical vapor deposition is a process where you have gases coming into a vacuum chamber, depending on the right chemistry, right pressure, right temperature, which is all adjusted and controlled. You have, let's say, methane gas coming in, separates out into carbon atoms, depending on a seed layer on your sample, forms the bonds and deposits on top of your sample as a diamond. I actually have a diamond coated wafer in my possession. I was doing some research way back a long time ago, and we got some diamond coated wafers from Naval Research Labs in Washington, D.C. So I'll have to try and find it in one of my boxes in the office. Anyway, coming back here. So increasing temperature creates more thermal energy, and then we have more carriers that are generated. So the next question that could come to mind is there a limit to the amount of carriers that are generated? And the answer is yes, it will taper off. Okay, so you can keep going up 500, 600, 700, 800, 900, 1000 degrees C, and it will taper off, it will level off. So there's a limit onto how many carriers can be generated, right? Now, all of this talk is so far only about intrinsic semiconductors, right? So now we come to the point where what good does this do us, right? At this point, we can't control it. Except for temperature, we cannot control anything. And even with the temperature, these quantities are not sufficient. Yeah, they are not sufficient enough for current conduction, right? It seems like silicon would have approximately 10⁻⁻10 free carriers at room temperature at 300 Kelvin, but 10^10 is a very small amount. Okay, that's not sufficient enough for current conduction. So what can we do? We need to increase the amount of free electrons or free carriers that are available to conduct electricity. And the only way we can have more carriers is by adding more onto them. Okay, and that's where doping comes into the process. The process of adding more carriers into our semiconductor is known as doping. D-O-P-I-N-G. You can't make this up. And the semiconductor which has material added to it is known as a doped semiconductor. Okay. So I'm going to skip the next few slides, and we'll revisit these slides after we are done with doped extrinsic semiconductors. Why does this keep happening? Drift current. What? Right. Let's try this again. Oh. Weird. Okay. All right. Semiconductor doping. So semiconductor doping, the process of adding external material to our semiconductor is known as doping. Okay. And the semiconductor is now known as a doped semiconductor or doped semiconductor, or what's the opposite of intrinsic? Known as an extrinsic semiconductor. Okay. And what we are trying to do here is to get our semiconductor to conduct, but we don't want it to become like a metal. There are certain applications where we would want it, but that's not here. We want to control the amount of carriers that are present in there. And if we can control that, then we can control how the device behaves, we can control how the device functions, and thus the rest of the circuit. And that is the fundamental operating principle of all modern electronic devices, or all solid state devices, right? Because we are able to add and create an extrinsic semiconductor, we can control the amount of current, we can control the voltage, we can control how the devices behave. Okay, so that's sounds like a sinister word, but with negative connotations. But in this case, control simply means, we are designing circuits to behave in a certain way, right? So how do we add these? Well, there are fabrication processes that we do, but the important question is, what do we add? Well, we want extra electrons, you want extra carriers to be generated. So we choose elements from column 3 and column 5 of the periodic table. Okay, so elements from column 3 and column 5 of the periodic table are chosen. And because we are adding these to a pure crystalline material, we define them as pure and impure. And so these are known as impurities or dopants. Impurities or dopants. In this case, again, impurity or dopant is simply means that we're adding, we had a pure silicon structure, or pure germanium structure, and we're just adding something that does not belong in there. That's all it means. It doesn't mean anything else. Okay. So how can we control it? Well, we choose the number of atoms that we're implanting in there, right? So we have a piece of silicon, we have a piece of germanium, we have a piece of semiconductor. We control the dosage. It's known as the dosage. We control the dose of the implant, right? And that's how we can control the creation of these devices. Just going on a little bit of a side note or a tangent, the actual process is known either as diffusion. There are actually two processes. There's diffusion and there's ion implantation. Okay. Ion implantation is a sort of a, for lack of a better word, violent process in a sense. We have an ion beam. Okay, so this process, there are two processes. Ion implantation and diffusion. Both, as the name suggests, implant and diffuse, meaning we're adding something, right? Ion implantation is requires a very sophisticated, well, not sophisticated, also very, very expensive equipment. Okay, in academia or academic research clean rooms, it's very rare to see an ion implanter. Diffusion is far simpler to perform. Yes. So I'm going to talk about that just a little bit. So ion implantation is you have an ion beam, you have your sample, and you're firing that ion beam at very high speeds onto your sample. So as I said, it's sort of a violent process. The ions, the atoms that we want to implant are going into the silicon lattice structure and are knocking the atoms out of your place. So there is real damage that occurs. Okay, it's not physical damage that we can see, but the silicon atoms are knocked out of their place. And that's, how we can implant in there. There are benefits to both. Ion implantation is the preferred process in industry, and it's a low temperature process. Okay, that's one of the big advantages. So if you have some sort of polymer or any kind of low temperature metal on your surface and you need to implant something, you need to introduce impurities, you want lower temperature, then you go with ion implantation. Also, you can control it precisely. Diffusion is not as easy to control in that sense. But diffusion is very easy to implement. You don't need expensive equipment. Okay, diffusion is like preparing a morning toast. Okay, you take bread, you spread butter on it, put it in a toaster. What happens? It melts and diffuses inside the bread. It's exactly the same process. We have a silicon wafer, we coat it with liquid material, and we stick it in a toaster, except the toaster is at 1,000 degrees C, and then we wait for an hour or 2 hours, however long we want, and then it slowly sinks in. And that's the process we perform in the clean room class. Okay, not 1,000 degrees C, we go up to 1,100, 1,100 degrees C, which is like approximately 2,000 degrees Fahrenheit. So we have furnaces, or our toaster goes up to 2,000 degrees Fahrenheit. All right, so we stick it in and it diffuses in there. All right, let's take a pause. Let me know if you have any questions. We'll talk about what happens after the impurities are in there. Now, somebody log on to Zoom and send me a test message. Otherwise, the meeting's going to kick me out. All right. I hope somebody's on there. Okay. All right. Any questions before we move on? Okay, so what happens? Let's say you have a column 5 element. Okay, column 5 element. Column 5 elements have 5 electrons in their valence shell or in the outermost orbit, right? So if you have 5 electrons and you introduce this element or the atom inside the silicon structure, I'm using silicon synonymously with semiconductor, but again, just processes for all semiconductors, okay? So let me just say you have so two of the most common elements that we use is phosphorus and boron, okay? So if we use column 5, you introduce it in there, it shares 1 electron each with a neighboring silicon atom. So it forms a stable bond. But because there's an extra electron, that extra electron has nowhere else to go. It is free to roam about. Okay. So that is indicated by this. There is an extra electron. So I want to say column 5 element. Let me change the color of the pen. So 1 extra electron. And this extra electron is not bound to any atom. It's not forming a covalent bond with any atom. So it is free to move around and available for conduction. It is known as a free charge carrier. The free in this sense is simply indicating that it is free to conduct electricity. Okay, so when we say free charge carriers, they're available for conduction. Okay. So in this case, if we take like 10 raised to 15, 10 raised to 16 number of atoms, which is still a small number compared to all of the silicon atoms that are available, 10 raised to 17, 10 raised to 18 is like an average dose. So the dose is defined as the number of atoms you're implanting per centimeter square. Okay, area, two-dimensional area. And so the dose is typically 10 raised to 16, 10 raised to 17, 10 raised to 18 atoms per centimeter square. So you implant that many atoms in a small space, you have that many electrons available for conduction. There are no extra holes that are created. The intrinsic carrier concentration is always equal. Number of electrons will always equal the number of holes as far as intrinsic generation is concerned. But when it's extrinsic, meaning you're introducing more elements or more atoms in there, now you're creating a large number of free charge carriers. Okay, these electrons are free to move around, and more importantly, no holes are created. Okay, no holes are created. It's just an excess of electrons and free negative charge carriers. So this atom that we have sent in the silicon structure, in this case from column 5, phosphorus, is donating an electron. Hence, it is known as a donor impurity because it is donating electrons. And then one more thing that is happening is, excuse me, because the electron has now left its atom, because the electron has left its atom, it leaves behind an extra positive charge that is bound in the nucleus of that atom, which is now fixed in place. Okay. So a donor atom or a donor impurity is a positively charged ionized atom. It has lost one electron, meaning it has now left with a positively charged. So it's a positively charged ionized atom. So donor impurities are positive ions. Because this has an excess of electrons, this type of semiconductor is known as an N-type semiconductor. Okay. Known as an N-type semiconductor. So the silicon samples that I passed around, some of them were implanted or had donor impurities. But the thing to keep in mind is when you take a sample like that, whether it's a dope or not, the number of electrons, even though they are excess and free to move around, are always balanced by the number of positively charged donor atoms. So it is charge neutral. Let's take a pause, think over all of that. Let me know if you have any questions. Any questions at all? Does it all make sense? Oh, which one? Oh, question being asked, is N-type semiconductor, does it stand for neutral? No, the N, and this is what my guess long time ago, is just for negative because it's negatively charged electrons. And so it's just N. So the N in the N type stands for negative. Okay. So we are only devoting, I mean, chapter 2 is devoted to the, device physics and all of that, but it is essential that we understand what is happening, right? And then from after this point on, we'll move into circuit analysis and how the diodes, how the devices function. But still essential to learn about this, yes. From the extra atoms that we're adding onto our semiconductor. So if we add silicon to silicon, nothing happens. If we add silicon to germanium, nothing happens. But if we add phosphorus to silicon, phosphorus has 5 electrons in the outermost orbit. And because it has 5 electrons, 4 of those electrons will form a bond with 4 silicon atoms. And the 5th electron is free to move around. That's where that extra electron comes from. That's where the extra electron comes from. Okay. So we talked about N-type. What happens? I'm guessing you should be able to name what would be the type if we add a column 3 element in there. The most common one is boron. And so B. So this is from column 3. So column 3 elements will have 3 electrons in their outermost orbit. What kind of semiconductor would it create? P-type for positive. But let's see how and why. Okay. So column 3 elements, such as boron, have 3 electrons in the outermost orbit. So it has 3 electrons that form bonds with the neighboring silicon atoms, right? So one bond or one spot is left open. And because it is left open, it is vacant, there is no charge associated with it, right? 3 electrons in a boron atom are balanced by the 3 protons that is inside the nucleus of that atom. But because there's an empty spot, and there are thermal carriers that are available, there are electrons that are moving around from the silicon atoms that will move into that spot. And so here there is a vacancy. And because there is a vacancy, there could be an electron that acquires sufficient energy, thermal energy, and jump from here to here. So it could make a possible jump. And what happens when an electron moves out of its spot? Leaves behind a hole. The hole has a positive charge. So leaves or creates a positively charged hole. And so when we add column 3 elements to our semiconductor, again, the same dosage, 10⁻⁻16, 10⁻⁻17, 10⁻⁸18 atoms per centimeter square, it will create that many corresponding free positive charge carriers. The process is slightly different from simply adding extra electrons, because in this case, there are no extra electrons. We are not adding holes. We are simply adding empty spots. That's the difference between P and N-type. In N-type, we are directly adding more electrons. We are adding more negative charge. However, in P-type, we are not adding any extra positive charges. Those positive charges are created because column 3 elements have only 3 electrons, meaning the 4th spot where the covalent bond should exist is now available for electrons in the silicon structure to jump into that spot. And when the silicon electrons jump into that spot, it creates an excess of positive charges. And so thus we have column 3 elements such as boron. The previous one was phosphorus, and excess of positive charges. And hence, this is known as a P-type semiconductor. And again, this is still charge neutral, or overall it is charge neutral. Any questions? Yes. So the question being asked is, why do we say it's an excess of positive charges, even though it's neutral? The excess in both cases, both p-type and n-type, simply refers to the amount of charge carriers that are available for free conduction, meaning they're available for free movement. And that's why we say that they're excess. Yes. So is the boron atom negatively charged? You're absolutely right. Yes. So the boron atoms accept electrons from the semiconductor, meaning they accept electrons from the silicon lattice structured atoms. And because the boron atoms are accepting an electron, they now have one extra negative charge. So these are negatively charged ionized acceptor atoms. Similar to the donor atoms. The donor impurities were positively charged, right? Because they are donating their electron, they lost the negative charge, they had the positive charge inside their proton, inside their nucleus, sorry. So the acceptor atoms are receiving a net extra negative charge, which is not balanced by their nucleus, and hence these are negatively charged ionized donor atoms, acceptor atoms. Okay. So these are important terms, donor and acceptor. This we're going to see just in the next slide itself, the notations and the equations. Okay. So acceptors are negative or negative ions. Donors would be positive. So far, so good. Okay. So charge carrier concentrations in an n-type material. Okay, in an n-type material, the number of electrons will be far greater than the number of holes. So n is greater than p, or if n is greater than p, that is an n-type material. In a p-type material, the number of holes will be far greater than the number of electrons. So if p is greater than n, then it's a p-type material. All right. So totally taken, the charge is neutral, but the free charge carriers, meaning the number of holes and the number of electrons in each type of semiconductor material, is unequal. Okay. So in this, N and P are unequal. Intrinsic carriers, they are equal, but extrinsically implanted or added on are unequal. And because they're unequal, there are terms that we use known as majority carriers and minority carriers. Okay. So in an N-type material, electrons are the majority carriers. So N and P are the minority carriers, or holes are the minority carriers. And in a P-type material, P, or the number of holes, are the majority carriers, and N minority carriers. Okay. The amount of carriers or the atoms that we are adding on is noted by uppercase N. Okay, so N with a subscript of D and a subscript of A simply indicates the number of atoms that we are adding on. And they are labeled as ND and Na. They are the actual number of boron atoms, phosphorus atoms, or arsenic atoms that we are adding on to our semiconductor material. Okay. Nd and Na. They're basically atoms per centimeter cube. These number of atoms that we choose are also known as dosage. So when we are creating these, when I was a teaching assistant for the clean room program a long time ago, this was at the University of Louisville, we used to send our silicon wafers, the student wafers, out here to California to get them ion implanted. So we would vacuum seal them inside the clean room in Kentucky and then fly them out or send them over here to California. There's a facility near LA that performs ion implantation as a service. Costs a few $100s to do it, but far better control than if you're trying to diffuse it in the lab itself. Okay, so much better device performance. And so we have to provide them the dosage. We'd have to tell them, okay, we want implant boron or phosphorus, and then this is the dosage we want you to use. There are all sorts of technical specifications we have to provide. Okay, so dosage is basically the number of atoms that we want to get implanted into our samples, right? And so ND and Na, it's always like 10 raised to 16, 17, 18, 19 atoms per centimeter cube. That's how we define them. Typical dosage would run from 10 raised to 14 to 10 raised to 20, 10 raised to 21 atoms per centimeter cube. Intrinsic carriers for silicon at room temperature is around 10 raised to 10. Dosage would be a little bit higher than that. So 10 raised to 14 would be considered a very low dose. Typical doses are 10 raised to 16, 10 raised to 17. Okay. Let me just put down 10 raised to 14 to 10 raised to 21 atoms per centimeter cube. Yes. Well, if you're looking at what? Extremely high. So the question being asked is, why would we want a extremely high dosage? Is that correct? Okay. So one of the most common applications for a very high dosage is to form contacts. So if you want to make contact with this, so we have micro devices, great, they work. But how do we connect our actual wires that we can take in our hand and make connection to that micro? We can't even see it, it's just so small. So to do that, we implant some metal on there. And for that metal to make good contact with the semiconductor, we have an intermediary layer that is of very high dosage. Okay, so again, does everybody understand? The question is, where would we apply, or why would we need very high dosage? Well, there are certain applications, but the most common application by far is to serve as an intermediary layer between our actual semiconductor device. So we'd have our N or a P-type material, and we'd implant a heavy dose material on top of that, just in a small area. And that would have almost metal-like properties. So heavy dose, meaning a lot of charge carriers, almost metal-like. And then that would make contact with an actual metal material, and so it provides a go between the outside world and the inside micro world. Does that answer your question? That's one of the applications. Right, 356. All right, other questions? Okay. Overall, if you have a device, it's governed by the charge neutrality equation, which is written right here. Q stands for unit charge or 1 unit charge. And if you multiply all the unit charges with the number of donor atoms, number of acceptor atoms, the total number of holes and the total number of electrons in any semiconductor or any doped semiconductor will always be charge neutral, turn out to be 0. This is known as the charge neutrality equation. Okay. ND minus NA or ND plus P minus NA minus N equals 0. Remember, intrinsic charge carriers, P equals N. Right? Intrinsically charged generated charge carriers, P always equals N. It's only after we introduce donor atoms or acceptor atoms that the charges could be imbalanced. But it's always charge neutral. Okay, so it's governed by this equation that is known as the charge neutrality equation. All right, let's see. Okay. We have equations for charge carrier concentrations for a N-type material. Donor atoms will be in far larger quantities than acceptor atoms. ND is always greater than NA. And so it's ND minus NA. For a P-type material, NA is greater than ND. So it's NA minus ND. Okay. When we're trying to solve, yes. So N is the number of carriers, yes. That's a good point. It gets very confusing because the same letter and symbol is used for multiple things. So in this case, yes, the N simply stands for the number of charge carriers. And this is going to sound funny or again, depends on how you look at it. N represents both N and P. Okay. If it's an N-type material, N represents N. If it's a P-type material, N is representing P. Here we have excess of electrons. And here we have excess of holes or positively charged holes. How much time we have left? Oh, we're almost out of time. Okay. In an N-type material, Na could be equal to 0. And a P-type material, Nd could be equal to 0. So that's always a possibility. Okay. So here, okay. Two final points. You're almost at the end. Intrinsic charge carriers are dependent on temperature. Extrinsic are independent. They depend on doping. dependent and independent. Sorry about that. Okay, so intrinsic charge carriers are dependent on temperature, whereas extrinsic are dependent on doping, and so it's completely independent of temperature. All right, so we'll end class here today. We'll pick up here again on Friday. We'll also revisit the other three properties that we need to look at, which is drift, diffusion, mobility, and velocity. Please keep up with the reading. I will post for the reading assignments and the next homework assignments shortly. Okay. Right. See you all on Friday.